thanks, Michel, for your introduction. So in parallel with the previous presentation, I will speak too about membrane and specifically about gas separation processing using the membrane technology with a focus on sweep mode configuration. So some words about the team. The team is composed of with Eric Fabre and Christophe Cassel, who are professors at the University of Lorraine, and they are, to be honest, they are the true brain of the team. I'm Roda BOUNACEUR, I'm a research engineer, and I'm in charge of the development of the numerical development. And Jasper Van Batten is in charge of the CAP-Open development. So for any question related to the CAP-Open development, please ask him. So we speak, okay. Now it's well known that membrane technology are useful and to separate gas mixture, and the membrane technology offers different advantage: simplicity, energy efficiency, environmental friendly, and compactness. On this topic, we have developed different code. The first one is named MEMSIG. MEMSIG is a numerical code which allows the simulation of multi-component gas mixture into a membrane. And you have different assumptions. He considers the isothermal process. He has several transport model inside. He has several transfer model as a constant permitted, dual mode of fluid gas, and is commercialized. We have developed a release, MEMSIG 2.0, with adding the Joule-Thomson effect. We have a module to estimate the pressure drop inside the membrane, and for now it's not commercialized. And recently, we have developed, with the help of Jasper, the sweep model. So this is a new tool. This module has the possibility to take into account the energy mass balance. He proposed the or countercurrent flow pattern, and we can take into account the pressure drop. So, in some words, what is a membrane? A membrane is like this. In fact, a membrane is just a box separated by a polymeric film here, and we have two sides, the upstream side and the downstream side. And in general, the pressure in the upstream side is greater than the pressure in the downstream side. We have one inlet and two outlets. One is named retentat, and the second one is named permeate. On the contrary, the model is here. We have in the sweep mode configuration, we have two inlets, the feed and the sweep in, and we have two outlets, the retentat and the sweep out. And on that case, the pressure in the upstream and the downstream are not linked. One could be greater than the other, or the contrary. In the industry, we have different applications of the sweep configuration. One consists on the recycle in the relate to the retentat flow rate. Part of the flux is like here to be entered in the permeate side. And the applications are gas drying, air conditioning, fuel cell humidification, or membrane energy exchanger. The second configuration available in the industry is a simple membrane where we can find one inlet, two inlets in here, and two outlets, the retentat and the permeate. Applications are carbon capture reflective membrane, high temperature reactive, or membrane gas contactor. And generally, the sweep is composed with air. The plan of my talk will consist of three cases with, I hope that will be wrote, with live presentation. The first case will consist on the validation of code against experimental data published on the publication of Zhu et al. The second case will focus on the contactor. And I will show you what is the benefit to using a suite mode configuration. And the last case will consist of the gas drying application. For each case, I will use different software. First one will do the ProSimPlus, the second one with Aspen HYSYS, and the last one with Aspen Plus. Our first case. So the Surreal have developed, published different experimental results. You have 3D this configuration. This is two membrane in series, and you have here rototile recycle flow after decreasing the pressure to go enter into permanent side, and we can modelize this process like this. This is the main inlet. The retentate inlet split into two flux. One go out. This is the retentate, the main retentate, and a part of this flux is re-enter into the permanent side, and this is the main outlet. Then the sweep out. He defined retentate recycle ratio as follows, and he proposed in the issue in this publication different experimental data. We represent the concentration versus the retentate recycle ratio. So I will do the same with the software. So to modelize such systems, I will use this process, and this is the description of this model with ProSimPlus. So we have the main inlet. You enter the sweep model. Here the outlet. This outlet is split into two flux. Here this is the retentate, the main outlet step. And part of this flux enter a valve in order to decrease the pressure and re-enter the membrane, and this is the sweep out. Okay, so if you double click on this module, note that you can, this module is available with the Thermo 1.1 or Thermo 1.0. It's enough. You hit this button, and you have the domain with the window appears. Here you have two different tabs: the operation, the components, and the second one are not important. Here you enter the configuration of the membrane, the membrane area, the membrane thickness. You can consider the counter current pattern or the co-current pattern, it's enough. And here you enter directly the pressure drop of the retentate side or the permanent side. And for now, for the moment, you just have consider just the constant permeability. And here you enter the permeability in terms of in Arrhenius form with taking into account the effect of the temperature. Now here this is the H0, and here is the activation energy. Now this is the value for the helium, and this is the value for nitrogen. So when you simulate such configuration, you obtain different results, and it is not important. I will not detail the result. What is more important is this. In fact, with such tools, we can measure the effect of, for example, the pressure or the split ratio using this possibility. Here, I will test the different result using sensitivity analysis by varying the split ratio from 0 to 0.9 with different steps, and I will record the different flow rate and the different mole fraction on the permanent retentate, for the permanent side and the retentate side. No, it's okay. And now we can draw the different calculation, and we can represent the variation of the mole fraction on each side versus the split ratio. And here, this is, okay, and here, these are the results obtained. In using this configuration, this is a mixture of composed of helium and nitrogen with this composition. We have the pressure above is 20 bar, and the downstream pressure is around 1 bar. And here we represent the different results. All the points are the points from the publication of theory R, and all the line is coming from the simulated result. So on the basis of this research, we can conclude that our code is valid. Second cases, I will try to show you the benefit of using a sweep membrane in the sweep membrane. Okay, using using the recent results of Hao et al. Was published an important study in 2014, and he has used different configuration of submembrane to show the benefit to use the membrane in the sweep configuration to remove different components. In fact, what is very important to retain on this publication is the sweep mode configuration is very important when you have a compound who has a high permeability value compared to the other compound. And to explain that, I will show this result. So here I will show a simulation using a simple membrane using our software MEMSIC, and I will compare the result with the same process but using a sweep model. For this example, I will use this configuration. This is constant permeability for the flux model. This is the contact current for the flow pattern. I use this area and this the downstream pressure and this thickness. For the permeability, this is the value. This is the values coming from the publication. Okay. And we use for the inlet the same configuration, the same value of the flow rate and the same composition and the same pressure. For the sweep model, I use the même surface, the même thickness, and the même validation, the même permeability values. When you do a calculation, here I will represent the value of mole fraction and flow rate for the outside, for the return residue or the permeate, or for the residue and the sweep out. And I have I put here the value of what you could name the removal CO2 fraction defined as follows. This is the flux of CO2 in the right to the residue and under the flux of CO2 in the inlet. Here you see that in the simple membrane configuration you reach a value of 1%, and in the sweep configuration with the same value of area and pressure you reach a removal fraction of more than 80%. So how could you explain these differences? In fact, I have put here the pressure, the partial pressure of CO2 versus the distance along the module. Here, this is the result right for the simple membrane configuration, and here the result with a sweep membrane configuration. And in fact, the driving force of the separation is located here. And in this configuration, you have here an important driving force here, but on the contrary, at the beginning of the membrane, the driving force is quasi null. On the contrary, in the sweep mode configuration, you keep an important driving force all along the entire length, and this is the reason that you obtain a better value of the removal fraction of CO2. In the publication, the author have studied the effect of the sweep ratio and the pressure ratio, and their conclusion is that the more the sweep ratio is, the more the removal fraction is important. And if we increase the pressure ratio, you increase the CO2 fraction. To illustrate that point, I have do the same with HYSYS. So this is the same configuration as follow. I put here the same inlet. This is consists on 1 bar, 1 meters cube per 1 number meters cube per second, and the composition is 10% of CO2. And for the strip, this is entered here at 1 bar, and when voilà. And the membrane area is equivalent to the results shown in the publication. When you do this simulation, what you obtain is here. You obtain mole fraction outside equipment close to 0.2%, and which is close of the result shown in the publication. And for the outlet, we obtain mole fraction of CO2 of 7.5%, which is close to the result present here. And concerning the molar flow, we obtain this value, and this value, if you translate in normal cube per second, they are closely equivalent to the result published in the shown in the publication. With such a model, what is interesting is to study the effect of the pressure, the pressure. So to do this, I have studied the effect of the molar flow of the strip and the pressure of the feed. I have made different screening from different ranges. So when you put the result, when you run the calculation, here the results. So we can plot the effect of the molar flow on the strip inside, or the effect of the pressure. What you see is if you increase the pressure and or the molar flow, you decrease the mole fraction of in the retentate side. So and this effect is what the author observed in their publication. Okay. Now, last case. The last case, right? This last case. In fact, for international company, we have studied the different real membrane coming from ECO, and this membrane are dedicated to gas drain. So the objective of the study was to study the possibility to use such a membrane in order to dry air gas with different constraints. To illustrate that thing, we use Aspen Plus models. So to modelize such a configuration, I use this process. This is the inlet enter into the SUP model. Here the one outlet, we enter a splitter. The splitter split this flux into two parts. Here this is the retentate. This is another flux. This flux enter a valve. This valve decreases the pressure from one person to another, and this flux re-enter the membrane, and here the outlet. For this simulation, I use this configuration. The membrane area is around 20 bar. The thickness is 1. We use the counter current flow pattern and no pressure drop in both sides. For the permeability value, you use this compound. And as I said previously, you see that the permeability of water is very more important than the other. So that on that configuration, this will be useful to use sweep membrane configuration. So if you launch the calculation, I will visit the previous. Okay, I run the calculation. So all is working well. So here we see the different results, and we can observe that the mole fraction inside was around 0.9%, and in the outlet we diminish drastically the mole fraction of water. So with such software, what is useful is to use to test the sensibility analysis. So I will activate it. Okay, no, so varying the mole fraction, the split fraction. This is the split fraction actually. From 0 to almost closely 1. I will define different parameters, and I will show the result versus the split fraction. So I will launch the calculation. Was it working well? And the results. Where are the results? Okay. So you obtain such a result, and you may plot different curves. For example, the variation of the mole fraction of different compounds versus the split fraction. And what you observe is that the more the value, the split fraction is important, the more the overall fraction of CO2 increase. What is shown here? Here I have put the removal fraction of water versus the sweep fraction. So now it's time for conclusion. Okay. Sorry for the. So in my conclusion lies in 5 points. So the first point is that important advantage of using sweep gas is to generate a driving force for membrane separation without an extra compression machine. And the opposite benefit is that it has an inherent feature of diluting the permeate, and in some cases that could be a problem. What is very important to note is that this point that it is very interesting to use the sweep mode configuration when you have a compound with a high permeability value compared to the other. That if you have to retain one point, it is that point. And more generally, the development of numerous tools such as MEMSIC or sweep as a capable in operation is a real asset for engineers who want to make optimization, revamping or process synthesis. Concerning our future development, we plan to, in the very short run, the development of equivalent tools for taking into account the gas liquid and the liquid separation. That's all for me. Thank you for your attention.